Hello, today we're going to talk about matrix multiplication. It's a little bit weird, but we're going to see why it's defined in the weird way that it is. And it has to do with solving linear systems. So on the first day of class, we talked about linear systems, and they look something like this, right? We've got the aij's, those are our coefficients. We've got x1 through xn, those are our variables. And we've got b1 through bm, those are the scalars on the right side of our system of linear equations. So all the x's live on the left, all the scalar b's live on the right, and the coefficients are the things that go along with the x's. So we want to rewrite this system of linear equations using a matrix. And the way we're going to do it is we're going to put the coefficients, all those aij's, in their own matrix. So here's A, it's the matrix of coefficients. And we're going to write the equation, the matrix equation, as ax equals b. And you'll notice on the left-hand side, we've got ax, which is matrix multiplication. So when we multiply a and x and do this out, we should hope that the entries of the matrix we get, so we'll get a matrix. The output of this multiplication is going to be a new matrix. And its entries should be those linear combinations of the x's on the left-hand side of our linear system. So they should be the left-hand side of the linear system above. So this kind of forces us to define matrix multiplication in a certain way so that we recover part of our original linear system. And then, of course, the matrix B, you can imagine the matrix B, it's just going to have the scalar b's as its entries. The matrix X is the vector, so here's B, we just wrote it down. And the matrix X is the vector of the n variables that we have. And so what we're saying is that we have m by n matrix A. We have X, which is an n by 1 matrix. And when we multiply those, we should be able to get the matrix B, which is an m by 1 matrix. And I want to draw your attention to some of the numbers that appear here. So notice that the number of columns in A matches up with the number of rows in X. So we've got a match here. And our output matrix B has the number of rows that A has m rows, and the number of columns that X has. So it has one column. So we already see that our matrix multiplication is going to be a little bit weird. We're going to need to make sure that the matrices we multiply together have matching numbers of columns and rows in a certain way, and the output matrix is going to steal its dimensions from part of our matrices that we're multiplying. Okay, so let's actually see then what this looks like in an example. And after this example, we'll get into the formal definition. So I've got this linear system here. It's got a variable of vectors that has 3 variables in it, or a vector of variables, not a variable of vectors, right? So there's my x. It has x, y, and z. The coefficients we read off from, let me grab a highlighter here. We read those off from the stuff that goes in front of the x's. That's our first column. So that's that column. And the stuff that goes in front of the y's, right there, that's our second column. And the stuff that goes with the z's, right, we've got 1z and negative 1z. That gives us our column for the z's. And the right-hand side gives us the matrix B, which I have almost written correctly, but you'll notice that I need a little transpose here, right, because that's supposed to be a column vector. So B should be the column vector 7, 5. Okay. Now, I want to figure out how do I multiply A and X, these matrices, to get a little matrix that's got the left-hand side of my linear system in it. And so let's take a look at what we're actually doing here. So what we are up to is, you'll notice that I take 3 and I multiply it with x, and I get a 3x there. And then I take -2 and multiply it with y, and I get a -2y that I add on to my 3x. And I take 1 and I multiply it by z, and I get a z that I add on to my 3x minus 2y. So what I did was I took the first row of A and I multiplied it by the first column of x, well, the only column of x, but that gives me the entry in the first row and first column of the product AX. Then I'm going to do the same thing with the second row of A. I take -3, 5, -1. I multiply with x, y, and z, and I add those things together. And I get the entry, so now I did, for my second thing, I did second row of A and then first column of x. I add up all of those things and I get -3x plus 5y minus z. And then, because of our definition of matrix equality, if AX equals B as matrices, that means that the first entry of AX is going to be the first entry of B, which gives us our first entry in our linear system, 3x minus 2y plus z equals 7. And same thing with the second entry. So -3x plus 5y minus z is going to be equal to 5. Okay, now this might be a little bit of a throwback, but do you remember the dot product of two vectors? If I take, let's say that I take a little example here. Let's say I take 1, 2, and I dot that vector with the vector -1, 3. What I do with the dot product is I just match up the corresponding entries. So I take 1 times -1, and I get -1. And then I take 2 times 3, and I add that to the first thing that I got, so I get plus 6. Okay, so that's, and of course, then we could add that together and we get 5 here. But what I want to point out is that we're kind of doing a dot product. We're just, instead of writing 1, 2 as a column, we could think about it as like a row vector that we'd have to transpose to get a column vector. And we'd get the same thing back. We'd match up the 1 and the -1, and then, so those get matched up, and then the 2 and the 3, those get matched up, and we'd get a -1 plus 6 equals 5. And if I did this with variables, if I took like 1, 2 transpose and dotted it with x, y, we're going to get something that looks a whole lot like a linear system, right? We're going to get x plus 2y. And that's basically what we're doing when we do matrix multiplication. We're doing a dot product. It just so happens that one of our vectors looks like a row vector, and we want to think of it as a column vector. So the way that we define matrix multiplication is we take the ijth entry of the product and we make it the ith row of A transposed dotted with the jth column of B. So that's right here. This is our formal definition. ijth entry, we take row I of A and column J of B. We dot them together, but of course, in order to do that, we've got to transpose the ith row of A. And that gives us a way of defining matrix multiplication that does what we want it to. And I've written this out with sigma notation, because the way that we actually do the dot product is we take, the first entry of one vector and the first entry of the next vector, we multiply them together, and then we add things up as we go. Now, if I actually look at what these vectors look like, the ith row of A looks like AI1, AI2, blah, 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 AI, let's see, I said we had K columns, so AIK. We transpose that and we dot it with column J of B, which is B1J, B2J up to B2K. I said that B had K rows, so they match up, right? That's why the number of columns of A and the number of rows of B have to match up, so we can actually dot vectors of the same size. And what's happening here is the way that I know which entries are getting multiplied is I've got this AI1 is the first entry of the ith row of A, and B1J is the first entry of the jth column of B. And so that's why in this summation I've got these L's that match up. If I wrote this sum out long form, it would look like AI1B1J plus AI2B2J plus blah, 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 plus eventually AIKBKJ. Right? And that's what the sigma notation is doing for us. It's just condensing that into a short form. There is a review of sigma notation in the book if you're feeling a little rusty on it. It's on page 17 of our textbook. Okay, so what you're going to do in class is do some practice multiplying matrices and figuring out which matrices can we actually multiply together and which ones can we not multiply together. So I'll leave that for you. And we're going to wrap up with talking about this very, 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 very useful theorem called the MVP. It really is the MVP of linear algebra. We're going to use it all the time. And we're going to prove this together in class. So that will be what we do together in class. We'll get some practice with matrix multiplication because it's a little bit weird. And then together we'll do a little bit of thinking about what the MVP says and then writing of a proof together. I will see you soon.